بسم الله الرحمن الرحيم.
Have you ever wondered why everything in nature seems so delightful to our eyes? As if carefully curated to capture our attention and arouse our curiosity to find the secret behind it? This beauty is due to the existence of fractals in nature. They're all around you, in the veins of leaves, in the waves of the oceans, in the pathways of rivers, in foam, in the sky when it's lightening, in the spiral structure of galaxies, and in countless other events in the universe. So, what are fractals? Fractals are shapes in math or geometry that have a special property called self-similarity. This means that even if you zoom in or out and look at different parts of the shape, you'll keep seeing patterns that look the same. To put it simply, a fractal is like a shape that repeats the same design no matter how close up or far away you look, showing patterns inside patterns. For a better understanding, let's imagine drawing a line and then dividing it into two branches, and then again divide every new line into two. And by repeating this process, you'll get what's called a fractal canopy. Interestingly, you can observe a similar pattern in a tree outside your window. This is indeed a fractal. Fractals exhibit intricate and detailed patterns regardless of the level of magnification. No matter how much you zoom in, the structure keeps revealing increasingly detailed features. They are often generated using simple mathematical rules or iterative processes. However, these simple rules can produce highly complex and intricate patterns. Some common examples of fractals include the Mandelbrot set, Julia set, Sierpinski triangle, Koch snowflake, the Fern fractal, and even the Fibonacci sequence. Fractals have applications in various fields including mathematics, physics, computer graphics, art, biology, and finance. So let's delve into some of these examples like Mandelbrot set. This set is named after the mathematician Benoit Mandelbrot, who was one of the first to study it in 1980. The Mandelbrot set is a fascinating and infinitely complex mathematical shape. It's like a captivating picture that's made using a special math formula. We're going to work with complex numbers. These numbers are made of two parts. A normal part like 2, minus 1, 3, and a unique part like 2i, minus 3i, and etc. Think of it as having two pieces of information in one number. For example, a complex number could be 2 plus 3i. Think of each point on our graph as having its own special number, and we are going to apply a specific rule to these numbers. The rule involves squaring the number or multiplying it by itself, and then adding the original number, which gives us a new number. After each application of the rule, we check if the number is growing too large. If it becomes too big, we stop the process for that particular point. We'll assign colors for each point based on how many times we could apply the rules before the number became too large. We'll repeat this process for every point on our graph, and for that we need thousands and thousands of iterations, which is indeed a lot of work for a human being. That's why we use computer coding to do this for us. And in the end, we'll come up with this: a stunning and colorful pattern known as the Mandelbrot set that looks like a mesmerizing piece of art, showing perfect circles of different sizes attached to a perfect cardioid at the main part of the pattern. It is indeed a captivating shape in the world of mathematics that keeps revealing new patterns and surprises you the more you explore it. For example, if we zoom to this part of it, we see circles on top of circles and smaller scales, and it goes out and forms this little tree made of 3 branches, every one of which is divided into smaller stems. Now the next one on the left branches into 5, and the next branches into 7, and then 9, 11, 13. Do you see what happens? It goes on and on with odd numbers. And on the other side, you have both odd and even numbers. Isn't that amazing? Just look closer and closer and it goes to infinity. Now let's take 2 numbers and add them. For example, 3 plus 5 equals 8. Do you see the number 8? Yes, here. Surprisingly, between every 2 of them, you have the sum of the both numbers. It is indeed remarkable, and it seems as if Mandelbrot set knows how to count and how to add numbers. Now come to the left side of the pattern. Do you see that little bump at the end of the spike? Let's zoom and see what it is. And when we zoom, that little bump looks like the entire Mandelbrot set. Oh, there's another one. Interesting. So if we zoom more and more, we get the same result again and again. Now at every age of the Mandelbrot set, we find different shapes that if we zoom in, we witness this repetition. For example, look what happens if we zoom here. A beautiful and mesmerizing pattern that repeats itself again and again. Now explore every corner of this pattern and witness the beauty of it. How can a simple math formula make such a perfect and at the same time intricate pattern like that? If you think that this beauty was made by Benoit Mandelbrot, it's wrong. He just put the formula and then he himself was surprised by the result of it. It's all a map of the numbers that's belonging to that formula when we just run it through that algorithm. Now what happens if we change the formula a little bit, like making it z cubed instead of z squared? Well, we'll get a different shape. And if you see, instead of those circles, we have cardioid all over the place. And if we increase the power of z, the shape keeps changing and changing. Now, can we find Mandelbrot patterns in nature? Well, the answer is yes. Here are some examples. Okay, enough with Mandelbrot set. Let's take another example of fractals, the Fern fractals. It's a well-known mathematical structure known as Barnsley fern. It's a fern of ferns of ferns. And this is again a self-similar pattern. Just like the Mandelbrot set can be created by a special function, the fern can be created in the same way but by 4 special functions. The first function will take any point and move it onto a line at the center. The next will move points up and a little bit to the right. The next rotates everything to the left, and the last one flips everything to the right. At this stage, it might not be clear how these 4 functions relate to the fern itself exactly. So let's do the same visualization again, but this time with a bunch of possible points on the fern itself. Here it's obvious that the first function creates the stem, the second creates successive ferns as we move up and to the right, the third creates the first leaf on the left, and the fourth creates the first leaf on the right. Putting it all together, it's a bit more obvious how these functions can create ferns of ferns. We write a coding for these 4 functions on computer, and the result that can be generated will look like this. Which means that this beautiful pattern is not an output of chance, rather someone has designed it using specific functions. And if we look to the world around us, we'll find numerous examples of this set of functions. Another example of fractals is the Fibonacci sequence, a pattern we previously discussed on a separate video which you can find on our channel. It's not only a well-known mathematical sequence, but it also holds a fractal nature. This sequence is prevalent in various natural formations. Fractals are everywhere. It seems like the universe is following some similar codes that repeat themselves again and again at every scale, just like hints for us so that we contemplate and find the truth behind them. After knowing all of this, let me ask a simple question. Why do fractals occur both in math and in our physical world? To be more precise, why does the nature follow mathematical laws? Well, coincidence cannot provide any explanation for this. Don't you think that someone deliberately put them there? I mean, think of it. This is a mathematical code which is deliberately written by someone, but this one is a real thing in nature. This is coded with a mathematical formula, but this one is found within our real world. Again, this is made by a mathematical code, but this one we see in our real world. Just look carefully. This is the outcome of a coding made by an intelligent man. And if you ask an atheist, he'll say it can't be randomly shaped by itself. But they say this one, which is in our real physical world, is happened by chance. Well, for me, it seems like arrogance. And this is exactly as Allah subhanahu wa ta'ala says,
وَمَا تَأْتِيهِم مِّنْ آيَةٍ مِّنْ آيَاتِ رَبِّهِمْ إلا كانوا عنها معرضين فقد كذبوا بالحق لما جاءهم فسوف يأتيهم أنباء ما كانوا به يستهزئون.
In fact, these occurrences, consistent with mathematical principles, can be viewed as compelling evidence of a deliberate and intelligent design shaping the beauty and order in natural world.
الذي له ملك السماوات والأرض ولم يتخذ ولدا ولم يكن له شريك في الملك وخلق كل شيء فقدره تقديرا.
The presence of mathematical patterns and principles in both fractals and nature is undeniably fascinating and thought-provoking. Mathematics, often hailed as the language of the universe, reveals intricate structures and concepts that are deeply woven into the fabric of reality. This revelation can strongly indicate the presence of an intelligent creator imbuing the natural world with a remarkable order and structure.
الرحيم